Hey, everybody, what is up? It is your chemistry teacher, Mr. Fabianski, coming to you live from it's a Bitmoji version of me at the chemistry lab. And you'll see one major problem with this is I do not have my safety goggles on. Shame on me. Thank you for pointing that out, guys. I appreciate it. Too bad Bitmoji didn't come up with the safety goggle portion of this. Well, anyway, let's continue on. I'm going to throw my face right up there so you actually see me. Let's continue on going through this. The resemblance is uncanny, minus the suit and the tie, but hey, whatever. So today we're going to continue our discussion on the foundation, the atomic theory, and formulating the models, getting through individuals such as J.J. Thomson and Robert Millikin, as well as Ernest Rutherford, looking at the experiments that they conducted and how that changed our model of the atom. So I hope you guys enjoy this, and I hope you learned something, and I will see you guys in the next clip. Hello everybody, and welcome. So we're continuing with our PowerPoint today with the foundations of the atomic theory. We're looking at progressing from Democritus and Aristotle through John Dalton. Now we're getting into J.J. Thomson, and J.J. Thomson brought a lot to the table. He actually gave us one of our first working models of the atom. So what he did was he used those things in the PowerPoint slide right there. That is a cathode ray tube or a Crookes tube. Now there are many different variations of the Crookes tube, but that one just happens to be one that is an empty tube. It's vacuum sealed, so all the air was sucked out. And it is hooked up to a cathode on one side and an anode on the other. When a high amount of voltage passes through that tube, it projects a beam. Now the beam is not light, instead it is charged particles. He did all of these investigations to see how those particles acted. Remember, we're going with Democritus. Democritus said that all matter is atoms. Atoms are particle. They are indivisible. So how are these particles acting? I'd like for you guys to watch this video here. I have that linked up. So I will join you right after this quick commercial break.
This is a cathode ray tube. Inside, there's nothing inside. It's actually a vacuum tube. So there's nothing but a vacuum on the inside. And it's called a cathode ray tube because this is the anode and this is the cathode. Right. When it's hooked up to an electric current, like I'm about to do here, you can see a beam moving across. You might think it's light, but when you take a magnet to light, does it do this? So you can see that it's bending or deflecting away from the magnet. So we know that it's not actually light. What J.J. Thomson summarized was that he was seeing a piece of an atom flying from one end of the cathode ray tube to the other, and that the piece of the atom that he was seeing was negative based on the end of the magnet that was causing a repulsion. So the negative end of the magnet was causing a repulsion, therefore the particles must be negative.
So I hope you enjoyed that video. From that video, we can make some observations. The magnet the gentleman was using was negatively charged at the point where he was bringing it down towards the ray. Since the ray was being deflected, we can assume that that ray, in fact, is itself negatively charged as well. Because remember, opposites repel, likes attract. Right? So a positive and negative would attract, while two negatives would repel. So we can assume, we can make the observation that that ray is negatively charged. We can make some observations. Now, J.J. Thomson also used different tubes, different cathode ray tubes or different Crookes tubes to make different observations and draw a couple different conclusions. So let's take a look one by one at his observations, and I'll explain to you what tubes these came from. The first observation he made was that the object in a tube casts a shadow. Basically, he had a tube that was made that shined a ray right through, and then there was an image. Now, as the ray hit the image, where it hit the image, it would be stopped. Where it was able to pass by the image, it would create a shadow on the back side, depicting an outline of that image. For number two, he used a different type of cathode ray tube or Crookes tube. This one had a paddle wheel inside, As the ray hit the paddle wheel would begin to spin and be pushed down the tube. So from this, we see that the particles of that ray have some force. They have some type of property that we'll see in the next slide. We saw from the video that the cathode rays are deflected by magnetic fields, and in fact, they are deflected away from a negatively charged field. So let's take a look at some of the conclusions in the next slide. The cathode rays are composed of particles found in all matter. They have a negative charge. They were later named electrons, and they have mass. From all of these, J.J. Thomson was able to make a working diagram or a working model of the atom. And that working model was the Plum Pudding model. No, not that plum pudding, this plum pudding model. So this is exactly what his model looked like. We had those small little particles, those electrons with a negative charge. We had a larger sphere that was made up of the positive charge, because we all know that atoms, they have to be neutral. Everything matter is not charged. It carries a neutral property. So if you have the negatively charged electrons, you also have to have some positive charge that cancels it out. And that is the pudding, the outside, that is positively charged. The electrons are negatively charged. Man, I am just moving around all over today. The electrons are negatively charged, while the electrons are held together loosely by the positive charged pudding. Continuing on, the next gentleman we're going to talk about is Robert Millikin. And in 1909, Robert Millikin conducted Millikin's oil drop experiment. What he basically did was he took oil droplets, he passed them through a charged plate, and then as they fell, he was able to observe them and adjust the strength of the two plates, the top plate and the bottom plate, to slow or speed up the fall of these charged oil droplets. All of this, in doing all this, he was able to calculate the charge of an electron. So J.J. Thomson told us that electrons were negatively charged. Millikin gave us the value of that charge. It quantified that charge. So if you watch this quick little video, it'll explain it a little bit more in depth than what I just did. Hope you enjoy.
Oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force. The rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E.
So after watching that video, we see that yes, the charge indeed was calculated. The charge of an electron is 1.6 times 10 to the negative 19th. C stands for coulombs. And the mass of the electron was 9.11 times 10 to the negative 28th grams. Now, the gentleman we're going to talk about next goes by the name of Ernest Rutherford. Ernest Rutherford again helped to develop the model of the atom further, but he was famous for an experiment he did, known as the gold foil experiment. So I think I want to show you that experiment first. So if you wouldn't mind joining me over in the laboratory portion of the classroom, we can get this going. So I will see you guys in just a minute. Hey, what is up, everybody? Welcome back to Fabs' Science Classroom. What we are going to recreate right now is the Ernest Rutherford's gold foil experiment. I have some paper balls that will be your alpha particles. I have some gold foil here, goggles. These are a very, very expensive piece of scientific equipment. I had to special order these. They came, it took me so long to get these, really a long time. A lot of money right here, a lot of money. Actually, they're just goggles with construction paper. But anyway, so we have our alpha particles. Those are the paper balls. Paper ball, just one. Alpha particle, gold foil. We're going to see what happens. All around us we have the detector, and we have the source that's emitting those alpha particles is right back there. So we're going to see what exactly happens when those alpha particles are shot at this gold foil. In 3, 2, and 1. Everybody, we had some great results from that. So, taking a look, actually a lot of alpha particles here. Taking a look, the gold foil was right here. I was the gold foil right here. The majority of those alpha particles went behind me. You can see all of those on the ground. They're all behind me. Now, some did hit me, some were deflected over to the side. But on a very, very small occasion, there's actually 2 right here. There's 1 even further back here, and there's 2 more even further back. On that small occasion, these alpha particles hit me directly, the gold foil. I was able to catch them and throw them back. Now, when they were thrown back, that means those alpha particles hit a very small area in the atom. Remember, the alpha particles are positive. Because they were completely deflected backwards, that must mean they must have hit something just like them, positive in charge. It's the nucleus. Those alpha particles that hit the nucleus bounce straight back. Yes, some were deflected. The majority went through, but there was a small amount that hit the nucleus, meaning that in an atom, there's a small, very small, dense, positively charged area that we call the nucleus. So that explains why some of them went back, but why did the majority of them go through? Well, Democritus was right. The majority of an atom is void, it's space. That's why the majority of these alpha particles went through. Everyone, thank you for observing Rutherford's gold foil experiment with me. Can't wait to see you again in Fabianski's science classroom. It was my pleasure, and we will see you all back in the PowerPoint. Hey, it's me, I'm back. Alright, so you guys just saw Ernest Rutherford's gold foil experiment. Ernest Rutherford did this in 1911. He shot alpha particles at thin gold foil. Those little fast-moving paper balls, those were alpha particles. Now I apologize, I called them electrons in the experiment when we were doing those. I apologize, that was my mistake. They were actually alpha particles. Now there's 2 properties of alpha particles. 1, fast-moving. 2, they are positively charged. So when they hit that gold foil, remember I was wearing that? That gold foil, they bounced back. Because remember, like charges repel. So the positively charged alpha particles hit the positively charged nucleus and bounced back. They were deflected. That's very, very important. So here's a little bit of a larger picture of what was going on. That was me standing in the middle. We saw the majority of those paper balls, those alpha particles, went behind, while some were deflected back, but a very small amount. It's due to the fact that the alpha particles, when they made contact with that small, very dense, positive center of the atom, the nucleus. J.J. Thomson gave us the electron. Ernest Rutherford gave us the nucleus. Going through, we made the observations. Almost all of the alpha particles passed through the gold foil unaffected. A very small amount of particles are deflected, and a very even smaller amount bounce back towards the source. From there, we can make our conclusions. Most of the particles bounce back because they are hitting, a small amount of particles bounce back because they are hitting that positively charged nucleus. The majority of them are passing through the empty space, the void. Remember Democritus? The majority of an atom is space, it's void. Moving from here, we can now adjust our atom. We started with the Plum Pudding model from J.J. Thomson, and now we have our first look at a nuclear atom with the nucleus in the center, positively charged, the majority of it being space, and the electrons are still dotted in there. This gave us Ernest Rutherford's nuclear atom. We have the positively charged nucleus in the middle. The majority of it is void in space. And then we have these electrons that are dotted around. Consider this. If the nucleus were the size of a basketball, and the electrons, they would be grains of sand scattered around the county. Okay? Think about a baseball in the middle of a football stadium, or a marble in the middle of a football stadium on the 50-yard line. That's your nucleus. The entire football stadium is the atom, and grains of sand, those are your electrons in the seats. The majority of the atom is void. Democritus was right. All right, everybody. I hope you have enjoyed this. Whoa, I'm moving around. I hope you guys have enjoyed this. I hope you guys learned something from the gold foil experiment. I will see you guys on the next video. Be safe.